All right, folks, it's time for our favorite podcast. And today I am bringing back Dr. Adam Leibovich right over here, this gentleman right here. Adam, how you doing?
I'm doing great. How you doing, Greg?
I'm excellent. Adam and I are both in Boca Raton, Florida, and we decided we were going to do this together. So we're going to run this on our normal audio podcast, but I'm also going to run this up on my YouTube channel so you guys can check us out, in action and all that stuff. Christmas, I believe, the topic of this discussion. Adam is a physics professor at University of Pittsburgh. I know you all know it, because Adam, how many times have you been on the show now? Did you count?
I did not count. I'm not sure.
I think we're over 10, but I basically ran about 10 shows with Dr. Leibovich here, Physics 101, basically the basics of physics with a couple of new stuff going on. And now we have some new stuff. As of Christmas, from what I understand, we have the James Webb telescope that was launched.
Mm-hmm.
And first of all, who is James Webb?
James Webb was a NASA administrator. He was in charge of NASA in the 60s. So that was a very busy time for the NASA space program. That's when the Apollo missions were taking place. And he was in charge of NASA during that time. And there was a decision a while ago to honor him by naming this telescope after him.
All right. So I grew up, telescopes, were those things that you just kind of like, oh boy, what am I looking at? I don't even, but it was something that I put in my hands on the ground, on Earth, and looked up in the sky. And now, I know that there's the Hubble telescope,
Mm-hmm.
and that's somewhere in the sky.
That is right.
So let's first talk a little bit about the Hubble telescope. What is it? What is it doing? And why have we gotten to the James Webb telescope?
The Hubble is one of the space telescopes that we have put up. It's not the first, and it's certainly not the last, but it was a very important one that was launched in the 1990s. It was supposed to launch earlier. It was launched in 1990. It was supposed to launch a little earlier, but there was some delays due to just getting it ready. And then there was the Challenger disaster, which delayed it further because it was brought into space by the space shuttle. And it is an optical telescope, so it's looking at light that is basically in the same frequency range as we can see with our eyes. It can go a little bit into the ultraviolet and a little bit into the infrared, but it also covers the types of light that we can see. It is a big telescope, but not a huge telescope, especially compared to some of the ones we have on Earth now, which are much larger. However, being in outer space is very advantageous for seeing things that are far away. And so that's one of the advantages of putting the telescope into space like we did with the Hubble.
All right, so where is the Hubble? What is it doing?
Mm-hmm.
And why do we have another telescope that we've launched?
The Hubble is in orbit around Earth. It is, I don't know exactly where it is, but it's circling around the Earth as we speak. It will continue to do so for quite a while. It started operation, like I said, in 1990, although initially there were some problems. I don't know if you remember, but there were some problems with the Hubble because there was the main lens was ground incorrectly, so it was not focusing correctly. But one of the nice things about the Hubble telescope is that because it was in Earth orbit, near Earth orbit, it could be serviced. And so there were a number of service missions over the time of the Hubble. Actually, during when there was the space shuttle, because the space shuttle would go up and catch the Hubble telescope, and then astronauts would do spacewalks and service it. And one of the things they did early on was fix the optics, but they also replaced older equipment with newer equipment and so on. The Hubble will have a end date because it the things in it that keep it running, that keep it pointing in the right direction. There's gyroscopes in there. They eventually fail, and unless we could figure out a way to service it again, which there's no plans to do, it will eventually no longer work. It also is in orbit around the Earth, but not so far away that it actually does feel a little bit of drag from the very, very wisps of the upper atmosphere, which causes it to essentially slow down. And eventually, if we didn't do anything, it would come and deorbit. It would fall into the atmosphere and then come and mostly burn up, but it's big enough that it wouldn't totally burn up. So this is something that I don't want to do. So eventually what they'll probably do is have a controlled re-entry so that any large pieces that survive coming into the atmosphere would land in the ocean as opposed to on land somewhere.
All right, so approximately how far from Earth is the Hubble telescope?
The Hubble is, let's see, I have to try to think about it. It's probably about 300-ish, maybe 340 miles, something like that, away from Earth. So it's high, but it's not terribly high. And that's actually probably from the center of the Earth, if I think about it. So it's probably well, something like that. It has to look to be sure.
So when they first launched the Hubble telescope, what was the objective, and has that objective been met?
The objective has been more than met. So the Hubble was designed to explore space. That's what telescopes do. And it has far outlived its initial planned lifespan. And it has sent back spectacular images over its more than 30 years in space at this point. And what it was designed to stare deep in space, but also you could look at planets that are close by. So, Jupiter, Pluto, whatnot, but look at galaxies, study supernova explosions. It's done all these things fantastically well. And one of the nice things is that the images that it sent back are all available. You can see tons and tons of images. I highly recommend just going to the NASA website. You can search NASA Hubble images, and there are hundreds of beautiful, beautiful images from outer space that were captured by the Hubble telescope.
All right, so I know in one of our earlier episodes, we talked about I think it was the exoplanets.
Mm-hmm.
And was that something that the Hubble?
That was not one of its primary missions, but it did look at some exoplanets. It's hard to see, really hard to see exoplanets visually. But Hubble has done some work with exoplanets. Probably the most important discovery that Hubble was part of was it collected lots and lots of supernova explosions, and using that, it helped determine the expansion rate of the universe. And as we talked about before, the universe is expanding, but it's also expanding at a faster rate. So it's actually the expansion is accelerating. And Hubble was one of the crucial instruments in getting data to come up with that result.
So while it's up, 300 miles away from the Earth, is it just randomly moving around, or are we sort of programming it to go left, right, up, down?
So it's in orbit. So the dominant motion is just the orbit that it happens to be in. It can be moved around, not only to point it in certain directions. It's a telescope. You have to point it where you want to look. So so we can move it to point it, but we could also move it slightly away from space debris. There's unfortunately a lot of space debris up there. So in case there's something that is coming close to it, they can move it around slightly so it doesn't collide with anything.
All right. So you said that it's basically outlived its intended life by a long time.
By quite a long time. Usually these things have like a 10-year expected lifespan, although you might hope that it would last longer, and it's lasted more than 30 years now. The nice thing, because you could service it, it was expected to live a little bit longer than you might expect if you just put something up in space and were not able to touch it. But it's lived longer than expected, even longer than some people think it should. And what I mean by that is it's still getting good data and it's still a very useful tool, but it was planned to be deactivated. And because it's so popular and it's done such a great work, there's been outcry to keep it running. And so its life has been extended even further than NASA had planned.
Is there an end date, or is it going to be still up in orbit until
the end date is gonna be there's an end date at this point, which is really just the lifetime that it can last without having more services missions and so on. And that is probably in the next 10 to 15 years. Somewhere in that time, the components will start to die enough that you won't be able to operate it anymore. If the gyroscopes go, which is how it orients itself, it won't be able to take any pictures anymore. And so it will probably live into the 2030s, and then we'll have to come down.
All right, so the James Webb telescope, is that going to interact at all with Hubble, or one thing has nothing to do with the other?
They're totally separate telescopes. The James Webb is the successor, you could say, to the Hubble, in the sense that it is also an optical telescope, although it's not that it's collecting light that we could see. It's actually collecting light in the infrared primarily. It captures a little bit of light in the red and orange part of the spectrum, but most of the type of light that it can see is in the infrared. And this is an important distinction between the Hubble and will allow us to do a lot of interesting new science that Hubble wasn't unable to do.
All right, we'll get to that in a second. I just want to kind of lay out the, it launched, what's the size of it? Let's talk about the launch of the James. I mean, is it like a spaceship where Cape Canaveral and boom, it just goes up into the atmosphere?
Pretty much, except for it wasn't from Cape Canaveral. It was shot. It's first of all, the James Webb telescope is a collaboration between NASA, the European Space Agency, and the Canadian Space Agency. So it was launched by the European Space Agency. So they have their own location where they launch their satellites from. And so it wasn't from Cape Canaveral, it was from, I believe, Papua New Guinea. And it was launched, as you said, on Christmas Day of 2021. So as of today, we're taping this. It is 20, let's see, how many days are we? We're 22 days into the mission at this point.
All right, so successful launch, no problems at all.
The launch was perfect. Everything so far, I must say, is worked extremely well. There's been no problems, which is very important, obviously, but also very scary. So one of the things about the James Webb is it is a gigantic telescope. It's much, much bigger than the Hubble, and they needed to curl the whole thing up to be able to fit in the rocket. There's no rocket that we currently have that could possibly launch it when it is in its full open form. Yeah. So they folded the whole thing up, and they had to unfold this thing, and there were many, many moving parts, and everything had to work well. And they're not done. They're still getting it totally into operating this setup, I guess you could say. So there's things that still need to move. There's still things they still need to
unfold.
Not so much unfold anymore. So that part is basically done, but they need to also get it into the spot and stop it. And so it's where it's traveling to, which we'll talk about. So there were what was called 29 days of terror. So yeah, from the launch until it gets to the spot and is pretty much in in the form where it can then get ready to start taking data. It's still going to be a while before we can actually take real data, but it's 29 days of terror with over 300 what they call single point failures. So if any of these things went wrong, then we'd be stuck.
Yeah.
So we're basically through all of them, thankfully, and everything's gone extremely well, no problems.
All right, so it's still in its launch.
It's still getting from from Earth to its final destination point. It, unlike the Hubble, which is very, very close to the surface of the Earth, the James Webb telescope is going to what's called the L2 points. There are these points, they're called Lagrange points, which are positions in the Sun-Earth system. So if you imagine the Sun and the Earth being two big masses, there's 5 sort of special points, and they're called Lagrange points, where if you put something in one of these points, there is an equilibrium. So the gravitational pull essentially of the Sun and the Earth essentially cancels each other out. And there are 5 of these, and this is going to L2, which is the second Lagrange point. The good thing about being there is if you're there, it's an equilibrium point, so it should more or less stay there. Problem is the L2 is actually an unstable equilibrium, so if you push it too far away, it would just go off into space. So you have to actually use some rocket fuel to keep it close by, but not very much. And so it's going to this point. It's a good point to observe because it follows the Earth as it goes around the Sun. And so in so doing, we keep it close to us, but it's away from all the Earth stuff. There's no worry about any of the stuff in near Earth orbit that could hit it. And we also need to keep it very cold, which is another thing we'll talk about. And so the L2 point is a very nice spot to locate it. It's almost there. At this point, it's about 90% of the way there.
Yeah.
The full distance is going to be about, let me think, almost 90,000 miles. Sorry, yeah, 900,000 miles away.
Yeah.
While the Hubble was like a couple hundred miles. This is 90,000 miles away.
Yeah.
So it's very, very far away.
So it's obviously further than the moon.
It's much further than the moon. And it's, because of this, we've sent men to the moon. We've not sent any humans farther than the moon. This is way farther than the moon.
Yeah.
So
farther than what planet is approximately that distance?
Well, it's still relatively close compared to the planet. So
Okay.
it's much closer than Mars. So we sent things, obviously we sent satellites and landers to go to Mars and go to the other planets and so on. So we've sent things, but we haven't sent people to this far away. And so servicing the James Webb telescope is currently out of the ability that we have.
So what happens if it needs servicing?
Unfortunately, there's nothing much we can do.
Yeah.
So they had to design it to last long enough to get good science. And unless we develop our rocketry and our ability to go there, there's not going to be any way to service it in any foreseeable.
Yeah. Are they working on that possibility, or is it's not even feasible?
It's feasible with this technology that we're coming up. I mean, there's actually going to soon be the launch of the Starship, which is SpaceX's big rocket, which is like much bigger than the Saturn rockets, which sent the astronauts to the moon. So that is designed to carry huge payloads to go to Mars. So if you listen to Elon Musk and SpaceX, they will be able to send people to Mars, which again is much farther away, fairly soon. So, you never know. We might be able to get to the point where we might be able to service it, but there's no real plans at this point to be.
All right, so let's talk about the size. Like, what would you compare it to size-wise?
Tennis court. I mean, it's huge. The size of the mirror is about 60-ish feet across. So, and it's not just one mirror. That's one of the things which makes it somewhat complicated, but also very cool. It's broken up into a whole bunch of different hexagonal smaller mirrors, which then all are aligned to make a big mirror, which again is about 60-ish feet across.
Yeah, and the last thing that I read was something about a sun shield that it's what's that all about?
Right. The James Webb is designed to capture light and take images in the infrared. Now, the infrared is part of the electromagnetic spectrum. It's not what we see, but it is just part of the infrared spectrum. Anything that has a temperature emits some light, some electromagnetic radiation. If you put like an iron into a fireplace, it will start off like black or whatever, and then it will start to glow orange. And if you heat up hotter, it will become white. That is the light, the thermal light that's coming off it. Okay. So when things are cold, it would be emitting in the infrared. So you and I, for instance, would be emitting in the infrared because we're not hot enough to glow white hot.
Yeah, not yet, at least.
Not yet. It's probably be a bad thing to start to glow white hot. So, so that means the telescope itself is emitting some radiation. They don't want that because that's not what they're trying to look at. They're trying to look at things that are out in space. So they need to cool the whole thing down in order to capture stuff that's out there and not just light that's coming off the telescope itself. To do that, they need to block all the energy that's coming from the sun because the sun is shining on this all the time, and that's heating up the spacecraft. So they developed this big sun shield, which is a huge long, it's a huge piece of some type of reflective material. And actually they have 5 layers of it with gaps in between to radiate the energy out. And on one side of this, it's getting all the heat from the sun, and they constantly point that at the sun. And the other side is where the telescope is located. So the telescope will point away from the sun, and the sun shield will block all the heat. So they have to cool the telescope side down to be really cold. They have to get it to be colder than about minus 370 degrees Fahrenheit. So unbelievably cold. So right now, the sun shield has been deployed, and the 2 different sides are becoming very different temperatures. It's going to take a while for it to actually cool all the way down to be below 370 degrees. You can go and look. There's a very nice website which shows you what's going on with the James Webb Telescope. Right now, on the hot side, the sun shield side, it's about 100 degrees Fahrenheit. It's still very cold. 100 degrees Fahrenheit is not that cold. But it's warm on the one side. On the other side, it is minus 350-ish or 330-ish at this point, and it has to get down to minus 370. So it takes a while because it takes a while for things to cool off in space. It can only get rid of heat energy by radiating away the same infrared radiation we were talking about, and that's a slow process. So it's going to take a while for it to cool down enough so that the telescope will be seeing things that are coming from far away as opposed to the glow from around itself.
Okay, all right. So I want to let everybody know I'm going to try to give you on my show notes some of the citations that we're talking about. So the one that you just mentioned here
Mhm.
right now, what will that enable someone to check out?
Well, it has a lot of information about the different parts of the launch, deployment, the unfolding of the whole telescope, what's going on currently, what still has to be done. So if you look at it in the next few days, it's going to show all that. And then eventually they'll have other information about what it's currently doing and trying to study and so on.
Will people be able to like live stream it and see what's going on at any particular moment?
I don't think so, but one of the nice things about this being a NASA telescope is all the data becomes public. So
Yeah.
that's why we got all these beautiful images from Hubble. Well, the same type of thing will happen from James Webb.
All right, so going back to where the L2 spot,
Mhm.
you expect that the spacecraft,
Mhm.
which essentially is what this is,
Mhm.
to be there in about a week.
From today, yeah, it's about a week. So on day 29, that's when they do the injection burn. So that's when they're going to fire the rockets to get it into essentially an orbit around this L2 point.
All right,
And that's on day 29. So that's a week from today.
so that would be January 22nd.
Today is the 16th.
Oh, that would be the
so
23rd. Okay, well, that would be my birth. The January 22nd would be my birthday. So, and I know all my followers here know that, and they're going to give me gifts. But in any event, so the 23rd, this show will be up already before then. So hopefully you'll listen to it, and then you'll be oriented to what's going on. All right, I want to take a real big step backwards for just people like myself that really don't know even really what a telescope is, what it does, how it operates. What's the basics of a telescope that I could go out and buy,
Right. So there's different designs of telescopes, but the main idea is you are collecting light, and you're either collecting that light by having it go through lenses, or this is having to bounce off of mirrors, and it goes into something. It could go into your eye, like the telescopes that we use on the ground when we're like amateur telescopes, or it can go into CCD camera, so you can collect the data like you would on your cell phone camera, or there's fancier tools that they have on these fancy telescopes where they might split the light into its different colors so they can study the different colors of the light they're getting and so on. So this has a number of different instruments on it, doing basically all those different things.
All right, so the lens, which is what I'm going to kind of conceptually understand this telescope to be basically utilizing to pick up these images and data, right? Is it just like pointed out in a random spot, or are they just waiting for things to come by? How does that operate?
Right, so they don't actually have a lens. It's a 3-mirror design, so they have and that's very good because they can basically get very clear images with the type of design that the telescope has. So there's a really big mirror, which is in this case made up of a whole bunch of different hexagonal smaller mirrors, and that mirror reflects light into a secondary mirror, and that secondary mirror reflects light into a tertiary mirror, a third mirror, and then the light goes into the instruments. Now, this big telescope is pointing out, and all telescopes would have a field of view. I don't know off the top of my head what the field of view is, so how much it actually sees in one spot, but this is a pretty big field of view, and they can aim it to be at certain places.
Yeah.
So it will look at different things in space. People can apply for essentially time to study different things in space, and if you get that time, the people who control the telescope will point it at whatever you are studying and leave it there for however long the observer being run would be for that object, and it will do different types of observations. It can look at particular galaxies. It can look at just stare at one spot in space. This is something that Hubble did. It's called the deep field image, where it just stared really intently at one spot, so it could see extremely faint things in this one area, and we were able to count how many galaxies were going really far back in time, because they're really, really faint from far away. And so you have to study and stare at one spot for a really long time to see these really faint things. The James Webb will be able to see things even further back in time. And that's because the light that's in the infrared, one of the reasons why they're studying, they have this being an infrared telescope, is when light is emitted, it travels through space. And as it travels through space, space is expanding. And that causes the light wave to expand as well. And it redshifts it, it said. It changes it from perhaps being something that our eye could see into the infrared. And so things that are really, really far away, the light has redshifted away from what, say, the Hubble could see, but the James Webb Space Telescope should be able to see it. So it should be able to see further back in time.
All right, so I want to go back to that, back in time concept, but I just want to make sure I understood what you just said. Anybody could apply to essentially utilize this telescope.
In principle, yeah, anyone could apply. Now you need to have
Credentials.
well, you need to come up with a good enough
Application.
application to win time on the telescope. This is how telescopes typically work nowadays. These big telescopes that we have on Earth or Hubble, you would apply for time, and then you need to basically win it in a open competition.
All right, and so let's just say you're lucky enough, or whatever, you have a great application and it gets approved, and you're doing your work. How does that play out? Do you have an obligation at that point to produce the results back to NASA and the European agency also?
Right, so they would get all the data, and that data would be public, but then you would get to take that thing that you were actually looking at. So you might be saying, I want to study a black hole at the center of this galaxy. So you're going to study, you pointed at that center of the galaxy. Now NASA will also have that data, but you get the data and you will then go ahead and try to analyze it to do whatever you're trying to study.
All right, wow, that's fascinating. All right, so going back in time, before we get to what the mission is of this telescope, and well, first of all, before we even get to that, how long? I know you say that it can't really at this point be maintained. So do they have like a life expectancy?
10 years is the initial time that they have. Again, it should last longer than that, and hopefully it will. And then they typically extend it longer than that. So I would imagine it will be more than 10 years, but the initial mission would be 10 years.
Yeah, so there's no robots on it or anything like that that could sort of assist with.
I mean, there's a lot of moving parts on it now to change the focus, or move the mirrors around to help focus it and so on. But if something breaks serious, then it's a problem.
Yeah. All right. So now let's talk about the going back in time. We're almost a million. This spacecraft telescope is going to be 1 million miles away from us. And you're talking about going back in time. Explain how that works. I mean, you're 1 million miles away. How does that change the time? Like today is January 16, 2022.
Yeah, so that's telescope's pretty close. So that's not really gonna matter time-wise. It will take a little bit of time for a signal to come from the telescope and get back to Earth, or if we send instructions to the telescope, it will take a little bit of time, but it's not that long. It will be on the order of probably a minute. I'm not sure. I'd have to sit down and calculate it. But the light that comes from, say, a galaxy is emitted from that galaxy whenever it's emitted, but it doesn't get to us immediately. It has to travel here, and the light travels at, surprisingly, the speed of light. And so if you imagine it's traveling at the speed of light, it will have to go a certain amount of time to travel that distance at that speed. Right. So distance equals speed times time. So you can travel a certain distance in a certain amount of time. The further away you are, the longer it's going to take to get to us. Another way of saying it, light that's emitted further in the past takes longer to travel to us. So by looking at things that are really, really far in the past, that has taken a long time to travel to us, a longer time to travel to us. So we will be able to, just because of the type of light that we're looking at, this infrared light, we'll be able to look at things which have traveled a very, very, very long time. And in that time, the light has shifted from the optical or whatever into the infrared. So there's a combination of things that we're going to be able to see due to the fact that the light has traveled this long time and redshifted. The James Webb telescope wouldn't be able to observe it. I should point out that there's other things that are in the infrared just in general in the universe, which are not necessarily from this redshift effect, that the James Webb telescope will also be able to see. So clouds of gas often emit in the infrared part of the spectrum. And so we'll be able to study things that are not necessarily way back in time, but just happen to be interesting effects, which are in the same frequency.
All right, so you explained to us before in an earlier episode about the universe is expanding. This thing is now going to be almost 1 million miles away from us. How does the fact that it's that distance help to validate or maybe, confirm these theories about the expansion of the planet? Or does that not have anything to do with that?
Where it's located, the altitude point? No, that's really just a convenient place to place the satellite.
Okay.
It's convenient because it is, like I said, it's away from the Earth, but it will orbit around the sun at the same rate. So it'll take it 1 year to travel around the sun, just like the Earth does. But it's far enough away that it doesn't have any of the effects of the Earth's atmosphere or light heat from the Earth. It doesn't need to worry about that. So it's a very convenient place to locate it, but it has nothing to do with validating in and of itself, right?
Okay, all right. So does it have a mission, or or we're just sending it out there and like whatever we figure out, and things are going to come across it, or is it a combination?
It's definitely a combination. So I mean, it is designed to study some of the earliest stars and earliest galaxies that the universe had. So going back to 10 or 12 billion years ago, studying galaxies and stars. These are when the first galaxies and stars were formed. Stars and galaxies were formed back 13 billion years ago. So the Hubble couldn't really see that because, again, the light had been redshifted. But the James Webb telescope will be able to see farther back and start to see some of these things. That's one of the main missions, but it will also study other types of things. It can look at exoplanets, try to understand atmospheres and exoplanets. So it has missions like that, or things that we hope to do with it like that, but other things might happen that we'll be able to use the observatory to see. So an example of that with the Hubble is not too long after the Hubble was in space. I can't remember the exact year, but there was a comet which hit Jupiter, and one of the tools we used to actually observe this this collision was the Hubble. So they saw that this was going to happen, and they aimed the Hubble at Jupiter for the collision time, and they were able to study what happened. That was obviously not something that they had planned for, because they didn't know about the comet beforehand. But with advanced enough warning, you can take one of these objects and point it to where something might happen, which would be out of the blue. So there will be some, almost without a doubt, there'll be certain things which happen which they had not planned for. That's one of the great things about one of these type of machines. They are so versatile and they can do so many different things that some unexpected science will definitely come out of it. But on top of that, there are things that are sort of planned, which are in the original designs were designed to study certain things, like these earliest galaxies.
Okay, so that's what I'm trying to wrap my brain around.
Mm-hmm.
Why is this telescope able to, look into the first stars, the first galaxies Is it its position? Is it the
It-
strength of these mirrors, or?
It's the size of it, so it will be able to collect light. These things that from early part of the universe, they're very faint. So you need to collect a lot of light or have a big area to collect this extremely faint light, I should say, to be able to get enough of a signal to see it. So
Yeah.
that's one thing. So the fact that this is way bigger, the compared to the Hubble or even telescopes on Earth, it's a very big telescope. Because of that, you'll be able to see very faint light. And then because it's looking in the infrared, it will be able to see things that have redshifted away from what the Hubble could see. So it's a combination of this big telescope is above the Earth's atmosphere, which is one of the reasons why another important thing, because the Earth's atmosphere absorbs a lot of light, so you wouldn't be able to observe infrared, the infrared spectrum like this on the Earth. So you need to get above the Earth's atmosphere. You need to cool it down. So it's the design of the telescope, the size of the telescope, which is going to enable us to really do this type of study.
All right, and so like the first stars in the first galaxies, why is that even significant? I mean, I guess a two-part question. And I know that you've kind of, talking about the expansion of the universe or whatever, that this really isn't, a mission to like figure out where everything started from and Big Bang and all that. But is the first stars and first galaxies, can I presume that because they were the first, that they have traveled very far away from us?
Yes. So in the sense that the ones we're going to be observing are very far away from us. There are the first stars. Let me back up. We have a very good idea about how things happen in the universe from like shortly after the Big Bang until now. However, a lot of those are just theories. And one of the things we want to do is to check our understanding and see if we need to modify our theories. So the first stars are very different than the stars that we have today, because the things that made up the stars was essentially only hydrogen, because that was the only element that was really around. And because of that, they actually were different sizes than the stars we have today, and they burn in a different way than the stars we have today. And so we have lots of good theories about how this works, but we don't have direct observational evidence. The other thing about these early stars is they went on, lived their lives, and then exploded and sent out all sorts of elements out into the universe, which then coalesced again into other star systems. And we are made of the things from those earliest star explosions. So the elements that make up Earth and our bodies and all that were made in these explosions from these early stars.
Yeah.
And so so trying to understand how all of that fits together is one of the reasons that we are studying this type of thing.
All right, so I know one of our episodes we talked about like I think we talked about like the 10 undiscovered mysteries of the planet. Are any of those part of the objective or the goals of this telescope?
Yeah, so I mean, we'll also be able to study things like early supernovas and other explosions. And so supernovas are very important because then you can use them to measure distances to objects in time. And this is how you can measure the expansion rate of the universe. So we'll be able to extend that analysis. So that is certainly one of the main things that big problems in physics. But there's other aspects of science which might not fall under the big 10 that I had listed, because I certainly have a particular slant. And understanding these early star formations and how galaxies work in general, and we now believe, actually thanks to the Hubble, that essentially all galaxies have a black hole in the center, and understanding that and studying more about black holes the James Webb Telescope is going to help us with a lot of those type of things too.
All right, so I did get a question. I haven't gotten a question from a while, but a man by the name of Barry Jaffe has sent me a question. He wants to know whether this telescope is going to help us discover whether there's a life on other planets.
That's a good question. I do believe one of the things that the James Webb Telescope is able to do, I'm not positive about this, but it could look at potentially look at atmospheres around other planets. So the advantage of or one of the things you might look for to find signs of life on other planets is things in the atmosphere of these planets which would not be made naturally except for by living things. So like one of the things about Earth is we have a lot of oxygen, and that oxygen is made by plants, right? Without the plants, the oxygen wouldn't have the concentration that we have in the atmosphere. So you can imagine looking for oxygen or other types of elements in the atmosphere, which are signs of life.
Yeah.
And there's no known chemical way for those things to arise other than by life. And I believe it can help with that. So it could.
Yeah. So you're going to see, so it could pick up the conditions necessary for life, but you're not going to see the little red man, floating around in his Tesla.
Unfortunately, probably not.
Okay.
Probably not. No.
All right. So explain to me how a telescope can pick up oxygen.
So the way you determine all these elements is by looking at the spectra of the light. So the light from an element, it emits light only in very, very particular frequencies. And every element has its own set of frequencies. And so by looking at the different frequencies that you're getting, you can say, okay, well, I see that there's an oxygen line, they say, and then an iron line, and then different lines in the spectrum. So you'll see a color coming, light coming at a very particular color, and then another one in another particular color, and that spacing would be particular to oxygen. Say.
Yeah.
So by looking at the spectra, the distribution of the colors of the light, you can determine the different elements that are there.
All right. Do you expect on January 23rd, when this telescope gets to its landing spot and everything is unfolded and everything is in operation, do you expect that the people at NASA and the European agency are going to be like, wow? Or is this something like just going to take a long time to figure things out?
I would say on the 23rd, they're going to say phew, because it all worked out and now they can start the process to get to the point where they're going to have data. So I don't believe the telescope at that point is going to be cool enough to actually take data.
Yeah.
They're also going to need to focus the telescope, so the mirror. So the mirrors, there's 16 these hexagonal pieces of the mirror, and they have to adjust them so that the mirror is actually focusing the light in the right direction. So it's going to be a couple months before they have like this wow image.
Yeah.
But I would imagine they are going to be relieved. Well, hopefully, if everything goes right, in a week from now, they'll be totally relieved that the telescope has gotten to the right point and everything's so far seems to be working perfectly. So let's hope that it keeps on working perfectly until that time and past that time. Then it's going to be a couple months of work to get it ready to start seeing images. They'll start to see really good images sometime between probably in about 3-ish months, probably 3, 4, 5 months. And then then I would imagine they're going to start to have unbelievable images coming out.
Yeah.
Similar to what Hubble has. This gorgeous images from looking at different things in the universe.
Are the Russians involved? Are the Chinese involved?
Not in this. It's like I said, it's NASA, Canada, so the US, Canada, and then a number of the European nations.
Yeah. So what's their take in though? Do you know? Are they like trying to do their own competitive telescope or?
I don't know of any large observatory like this that either of those agencies are planning. Right now, China is focusing a lot on near Earth orbit, and then eventually, moon, and then presumably they'll be interested in Mars, but they are working on their own space station. And they sent a rover to the moon, which is working on the dark side of the moon right now. So that's one of the things that they are focusing on. I don't know what the Russians are currently focusing on, other than the continued operation of the International Space Station. They are partners in that, along with us. So I don't know if there's anything else what else they're working on at the moment.
Okay, so have I missed anything that you think we should cover in this episode?
No, I think it's just very exciting, and I expect, just like the Hubble, this is going to be a fantastic observatory. It's going to get unbelievable number of beautiful pictures out that we can all enjoy, and that's for the people who are just enjoying it, but then there'll be tons of amazing science that comes out of it. So
sounds very exciting. All right, guys, that's going to be that's it for this episode. Hey, Dr. Leibovich right over here. Good looking guy, huh? All right, so I'm not going to tell, no calls to action here. I'm just going to say this on my show notes. I'm going to give you the YouTube channel so you can see us. If you're hearing us and you're like, wow, I hear you guys are on YouTube. I'll give you that. I'm going to give you Adam's bio, and I'm going to give you the links so that you can follow the information as it's provided by NASA. Is it NASA?
this is NASA, yeah.
Okay. All right. So that's it, folks. Everybody, listen, look up in the sky. It's a spectacular place. Maybe you go get a telescope. All right. But you got to tune into the show to get this kind of information. So Adam, thank you.
My pleasure.
Let me shake your hand.
All right.
All right. And that'll be it, folks. So have a good day.